Essential Science, Chapter 2, Atoms, Molecules, and Ions, Lesson 2. So looking at a molecule and what we call a molecular compound. So molecules are a discrete unit of atoms that have bonded together. Molecules are typically those atoms that are going to share their electrons as opposed to giving or taking electrons to become more stable. So once again, a molecule can be a compound, but sometimes a compound is not a molecule because a compound has to be two different types of elements. But we see here that in what we call diatomic molecules, meaning two, we're talking about two of the same atoms. And these are how these particular elements exist in nature. So I have those highlighted: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So this means that their elemental form is H2, N2, O2, F2, Cl2, Br2, I2. They are never found alone in nature. They always have their buddy with them. So polyatomic means that we're going to have three or more different types of, or three or more atoms. They can be different, they can be the same, coming together to form a particular type of compound. So how can we represent compounds? Well, your chemical formula is your simplest type of formula, and that is going to tell you the number and type of particular atoms that are present. Your number of atoms are always shown by a subscript, and then your atom itself, what element that represents, is by its one or two letter symbol. So your molecular formula is your true formula for a particular compound. So this is how this exists. It's NH3. There are 3 hydrogens for every 1 nitrogen. Carbon tetrachloride, 4 chlorines for 1 carbon, hydrogen peroxide, water, hydrogen. So this is how the molecules actually exist. We can also consider a formula called the empirical formula, which is the simplest whole number ratio of atoms in a compound. So hydrazine, N2H4, can be simplified to NH2. So what did we do? We divided each of these by 2, and now we have the simplest whole number ratio. This does not necessarily mean that this molecule can exist. It is just a simplified form of a molecular formula. So looking down here, sometimes the molecular formula and the empirical formula are the same. Sometimes they are different. N2O, we cannot divide this by a number and make it any simpler. So this is both molecular and empirical. C6H12O6, which is a molecule of sugar, glucose. C6H12O6, we can divide all of these through by 6 and get CH2O, which is a carbohydrate. Carbon plus a water. That's where we call them carbohydrates. H2O2, hydrogen peroxide. Once again, we can simplify this to just HO by dividing by 2. Now, HO doesn't necessarily exist, but it is the simplest whole number ratio for this particular compound. And then we have water, H2O. This is both empirical and molecular formula because we cannot simplify this any further. So your structural formula is going to give you the most information about a particular compound because it shows you how the atoms are actually connected. So it's going to show you what type of atom, how many there are, and then how they're actually bonded to each other. So your perspective structural formula, we use wedge lines and dashed lines to show on a sheet of paper what atoms are going away from you, which is your dashed lines, and what atoms are coming towards you, which are your wedged lines. Your ball and stick they have different colored representations of these spheres, right? That says if you're purple, you're most likely phosphorus. If you're green, you're some type of halogen. Hydrogen is normally white. Carbon is black. Oxygen is red. Nitrogen is blue. And then you show them with a stick connected to another sphere. So your space filling then is going to show you the actual comparative size of these particular atoms, and once again, how they are connected to each other. So ionic compounds occur when you actually have a transfer of electrons. This transfer is always from the metal to the nonmetal. So the metal gives up the electrons, the nonmetal accepts them. And then because we've given up electrons, we become positive. If we take on electrons, we become negative. So now we have opposites attract. The positives are attracted to the negatives, which then we call electrostatic forces. So that's how ionic compounds are held together. Over here, I'm showing a piece of sodium being burned in chlorine gas to form sodium chloride. So what's happening? Well, sodium atomic number 11, we start with 11 protons, always, and 11 electrons. Chlorine atom starts with 17 protons, always. We're not changing the protons, but it has 17 electrons to balance out. We always start neutral. Well, if sodium gives up one electron, it has the same electron configuration as neon. So it's become more stable. It gives up its electron to chlorine so that when chlorine accepts an electron, it has the same electron configuration as argon. It becomes more stable. When something loses an electron, it actually shrinks in size. When something gains an electron, it grows in size. But now we have something that is positively charged, negatively charged. They come together through electrostatic forces to form a crystalline structure, an organized repeating pattern, which we call a crystal lattice. And we know by looking at a piece of salt that it's a tiny white cube. So this is what happens. There's repeating units of positively charged sodium atoms surrounded on all sides by negatively charged chlorine atoms. And it just repeats until the crystal itself gets too big, and then it cleaves off and it just forms a new one. So any type of ion is simply a charged particle. It's got to have a charge with it. That's what we call an ion. So if you're a cation, you're positively charged. The T in the middle of cation is a positive. The T looks like a plus charge. So cations are always positive. Cations form because an atom gave up electrons. Typically, it is going to be the metals that do this. So cations are positively charged metals that gave up electrons. Anions are the opposite. A negative ion, so the N in anion stands for negative. It also stands for nonmetal. So a nonmetal becomes negative when it accepts an electron. Therefore, cations and anions are attracted to each other, positives and negatives. Monoatomic ions mean that you have only one atom with a particular charge. Polyatomic means that you have a group of atoms that take on a charge on the overall molecule. So in looking at our periodic tables, we've been talking about charges and how can we know what charges certain things take. When we look at our main group elements, all of those A's, so we ignore the transition metals, which are here, this kind of pond. If you're a group 1 metal, you're always +1. If you're group 2, you're always +2. If you're group 3, you're always +3. Now, group 4 does a little weird things. Tin and lead actually can be +2 or +4. Carbon has its own branch of chemistry, but it can take on a -4 charge because it's a nonmetal. So then our nonmetals here, nitrogen and phosphorus, 5 is 3 away from 8. It takes on a negative charge. 5 minus 8 tells us group 5 is -3. Group 6 nonmetals and tellurium take a -2 charge. 6 minus 8, -2. Group 7 nonmetals take on a -1 charge because 7 minus 8 is -1. So all of these have a set defined, I'm only going to have one particular type of charge. This is always the way I'm going to behave. So if you learn how to read your periodic table, then you know that this is just the charges that these particular elements take. In the middle, we have transitions. They are transitioning between different charges. Chromium can be +2, +3. We also see chromium 6, which is a hexavalent, and that's the stuff that's extremely poisonous. So here we have chromium through nickel. We have 5 elements in a row here. 2 plus 3 is 5. All of these elements here take on either a +2 or a +3 charge. Group 11, aka 1b, all take at least a +1 charge. So copper 1, silver 1, gold 1. Then copper can also be +2, gold could be +3. Silver is always a +1. So even though it's in the transition metal pond, it's always a +1. And then we have our group 12 or 2b, always have at least a +2 charge. Zinc, cadmium, and mercury. Now, mercury is special because it can form a diatomic cation. So it's actually polyatomic. There's more than one atom there. And this is what we would actually call mercury 1 because you have 2 atoms with an overall charge of +2, which means each individual mercury atom has a charge of +1. So we looked at the periodic table. We can also see here that if we go along this diagonal towards aluminum, we're either counting up or counting down in terms of our charge, +3, +2, +1. So these are always those charges. So even though it's in the transition metal pond, zinc and silver will always just have 1 charge associated with them. The other transition metals have varying charges as well, and they are similar to what their specific group will do. So how do we determine the formula of an ionic compound? We simply call this the crisscross method because you look at the charge on the cation, you look at the charge on the anion, and then you simply pull the number down and make it a subscript. So here we have aluminum oxide. Aluminum is a +3, oxygen is the 2-. The 3 comes down, the 2 comes down, and now we have a balanced charge. All ionic compounds have to have an overall charge of neutral, has to be neutral. Charge is 0. So what is this saying? If I have 2 aluminum atoms with a +3, that gives me 2 times 3 is 6. If I have 3 oxygen atoms that are -2, I have 3 times -2 is -6. 6 minus 6 is 0. We can also do this with polyatomics. Calcium is a +2 charge. The phosphate ion is -3. I can pull the 2 down, I pull the 3 down, I've balanced out my charges. When you have a polyatomic and you have more than one of them, you have to make sure that you include parentheses to show that it is 2 of the entire group that is required. You wouldn't just write PO42. That would mean you'd actually have 42 oxygen atoms. That would be incorrect. The parentheses say I need 2 of this entire group because the entire group holds the charge of 3-. But once again, this crisscross method is going to work no matter what. Keep it simple, look at your numbers, pull them down. You never pull down the actual negative or positive sign because you cannot have a negative number of atoms. Remember, these subscripts tell you how many of a particular atom is present. We can't put a negative in front here because there's no such thing as a negative, you can't have negative number of atoms. They either exist or they don't. So naming ionic compounds. You always have the cation first, no matter what. When we look at the periodic table, metals show up before nonmetals if you read it like a book, left to right, metals before nonmetals. So the metal retains its name, you do not change it. If it is what we call a binary compound, which means you only have 2 different types of atoms present, one specific metal, one specific nonmetal. Now, we're not talking about the number of those atoms, just that there are only 2 of them. Then the nonmetal changes its ending to "ide." Oxygen becomes oxide, hydrogen, hydride, nitrogen, nitride, sulfur, sulfide, etc. If you have an anion that is a polyatomic, which oxyanions means that we've got a nonmetal bonded to a bunch of oxygens that have a total charge on them, you're going to not change the ending. It's either ate or ite. If you have nitrate, it's nitrate. You have nitrite, nitrite, phosphate, sulfate, carbonate. So you're not changing the ending because the polyatomic itself already has a name. We employ the crisscross method to make sure that if we say, hey, what's the compound that's going to form between magnesium and fluorine? Well, we know it's going to be magnesium fluoride, but we can determine to make sure that we have the correct number of atoms. How is this different? Well, what if we have iron and fluorine? Well, we'd have to know, because iron is a transition metal, whether it was iron 2 or iron 3. So transition metals will either take an OUS or an IC ending. The OUS ending is always the smaller charge. The old school was when we had to know Latin, and therefore we had to know the Latin names of elements. Iron is Fe because it was ferrum. So ferrous means +2. Ferric means +3. An easier way to represent this, which I call the new school method, is to use Roman numerals. So we would say iron parentheses Roman numeral 2 or iron parentheses Roman numeral 3. Therefore, by looking at the name, if I say chromium 2, I know chromium's a +2. If I say chromium 3, I know chromium's a +3. But it's always metal, then non-metal. If you only have one single non-metal, it takes an IDE ending. If you've got a polyatomic, it keeps its name. And we never, ever, ever use Roman numerals on things that are not transition metals. So I would never say sodium 1 chloride, because sodium's always a +1. You only use those Roman numerals when it is an element that can do different things. So naming ionic compounds was looking at how do metals and nonmetals come together, or how does something that's a cation and an anion bond, and how do we name it? Well, now we have to know how to name acids. Two different things to look at. A binary acid, once again, binary means 2. Your first element is going to be H. That's what makes something an acid, and H is going to show up in the front. Your second element is what it is. It's not going to be oxygen or nitrogen. Those are exceptions, because hydrogen bonded to oxygen is just water, and hydrogen bonded to nitrogen is ammonia, which happens to be a base. So all other nonmetals, you are always going to say hydro, look at the nonmetal, sulfur, and then add an IC ending. So hydrosulfuric acid means that I have H2S. Your crisscross method is going to work the same way in determining how many hydrogens do you need for a particular anion. Your nonmetals have a negative charge. Hydrogen is going to be a +1. So it's really pretty simple. If you have something with a -3 charge, it's always going to be 3 hydrogens. If it's a -2, you add on 2 hydrogens. If it's a -1, you add on 1 hydrogen. But for binary compounds, you will always say hydro in the beginning and ic at the end, and then say acid. So oxyacids are looking once again at those polyatomics where you have a nonmetal that is bonded to a certain number of oxygens. Nitrate, nitrite, sulfate, sulfite, phosphate, perchlorate, chlorate, chlorite, hypochlorite, all of those polyatomics. So once again, you're adding on a certain number of protons, which is just an H+, right? Why is it called a proton? Because a hydrogen, if it's lost its electron, all that remains is a proton in its nucleus. It has no neutrons. So now we're just looking at changing the endings. If it's phosphate, it becomes phosphoric acid. If it's sulfate, it becomes sulfuric acid. Nitrate, nitric acid. Then the ones that are ites become us. So nitrite becomes nitrous acid. Sulfite becomes sulfurous acid. Phosphite, phosphorus acid. So the ates become ics, the ites become us's. And then we always just simply say acid. Last thing to talk about naming is looking at molecular compounds. So once again, these are going to be groups of nonmetals that are going to share their electrons, because it doesn't make sense for one of them to try and give up 5 or take on 7. It's just easier to share when you have a lot of electrons. So your first element will always be found farthest to the left and towards the bottom. This is because this is typically going to be the larger element, which is then allowing for the smaller elements to bond around it. These are always going to be binary compounds. So you'll only have two different types of nonmetals or potentially a semi-metal and a nonmetal. But molecular compounds will never have metals in them. So when you're looking at a substance and you see a metal show up, under no circumstances do you give it a prefix, right? We talked about ionic bonding and ionic names, right? No prefixes. Just like, however, with ionic compounds, your second element will take the IDE ending. So you leave the first element alone. You just state its name. If there's more than one of those particular atoms, then you indicate that with a prefix. Your second element will always have a prefix indicating the number. So even if there's just one, you will say that. So we use our prefixes to determine or to tell how many of a particular type of atom is present. Because in molecular compounds, the bonding does not occur based on charges. Things are not balanced out in terms of charges. So we don't know. There are things that can form, nitrogen and oxygen can form multiple compounds. Dinitrogen monoxide, meaning N2O. Nitrogen dioxide, meaning NO2. Dinitrogen tetroxide, meaning N2O4. Nitrogen and oxygen can form all kinds of compounds, and it's not based on charges. So mono can be omitted for the first element. Carbon monoxide, CO. We don't say monocarbon monoxide. And for oxides, the A and typically the O will be omitted in the prefix. So we don't say monooxide, or if you look at it and you put it together, it looks like monoxide. We don't say that. We don't say pentaoxide. We just say pentoxide. So we drop the A's and we drop the O's. So summarizing here. Compounds, ionic versus molecular. Ionic means that we have to have a metal, or we have the only polyatomic that we're concerned with that has a positive charge, which is the ammonium ion. So a metal has to show up first. That means we're following ionic nomenclature. If your cation only has one charge, we just name the metal, and then we will name the nonmetal by changing the IDE ending. Or if it's polyatomic, we keep the name of the polyatomic. If we see that the metal has more than one charge, meaning it's a transition metal or tin or lead, then we have to say lead 2 or lead 4. And then once again, the nonmetal changes its ending to "ide," or the polyatomic keeps its name. If you have binary compounds of nonmetals only, or nonmetals and potentially a semi-metal, this is the only time that you use prefixes. So we use those prefixes to show how many of a particular atom is present, and the ending on molecular compounds will always be IDE. So you're never going to have a molecular compound that is ending with an 8 or an ite. We also know that there are some common names of particular compounds. And then, of course, we always have a systematic name that is associated with things. So we know H2O is water. However, we would name that dihydrogen monoxide because there's 2 H's, 1 O. Ammonia, trihydrogen nitride. Dry ice, carbon dioxide. Solid, right? Otherwise, it's CO2 that we breathe out. Sodium chloride, table salt. Dinitrogen monoxide is known as nitrous oxide or laughing gas. Calcium carbonate is marble or chalk or limestone. Sodium hydrogen carbonate, which we can also call sodium bicarbonate, is simply baking soda. We'll talk about hydrated compounds later, but what this means here, there are actually 7 water molecules that are associated within this crystalline structure for the ionic compound of magnesium sulfate. So the technical name is magnesium sulfate heptahydrate, but we just call it Epsom salts. And then magnesium hydroxide is milk of magnesia. keeping in mind that we would never say magnesium dihydroxide. Why? Because when I see this metal shows up, I never use a prefix. I also notice that magnesium is a group 2 metal, so I never say magnesium 2 because it can only be magnesium with a +2 charge. So I don't have to say that in its name because it can't be anything different. So the last part of this chapter is dealing with an introduction to organic compounds. So organic chemistry is studying all the different ways that carbon can bond to itself and to some other nonmetals like nitrogen, oxygen, hydrogen, sulfur, and some halogens. So hydrocarbons are your simplest type of organic compounds. Hydro meaning hydrogen, carbon meaning carbon, so you only have 2 different types of atoms present, hydrogen and carbon. Your simplest is going to be a singly bonded, so these are called alkanes. When you double bond, you get alkenes. When you triple bond, you get alkynes. And then you have a special type of compound, which are called aromatics because they have a particular odor associated with them. And these are alternating single bonds and double bonds within a ring structure. So isomers of a particular compound is when you have the same chemical formula, but you can build different structures. So over here, we have an example of ethanol and dimethyl ether. Same molecular formula. If you count it out, I have 2 carbons, I have 6 hydrogens, 1 oxygen. 2 carbons, 6 hydrogens, 1 oxygen. These are called isomers because we notice here that my oxygen is bonded to a carbon and a hydrogen, whereas here the oxygen is bonded in between 2 carbons. So these are 2 completely different compounds. They behave 2 completely different ways. Ethanol is the alcohol that is found in liquor drinks, beer, whatever, wine. You can drink it. Dimethyl ether is used as an anesthesia, so it'll knock you out. So what are some derivatives of alkane? So this is keeping in mind that an alkane is a carbon that only has single bonded carbons in it. So only single bonds between things. Do you have what's called an alkyl halide, which means we introduce a halogen, fluorine, chlorine, bromine, or iodine. Alcohols means that we're going to replace one of the hydrogens with an OH group. Ethers, we have a single bonded oxygen in between 2 carbons. And these R's here are just representing any generic group of carbon. Amines, we have nitrogen bonded. Thiols, we introduce an SH group similar to an OH group, but these alcohols and thiols have different properties. And sulfides are similar to ethers, where we've replaced a carbon that sits in the middle with a sulfur or an oxygen. So some other important organic compounds. Now we're looking at things that can be double bonded. So aldehydes, ketones. Aldehyde is when you have a double bonded oxygen at the end of a carbon chain. Ketone is when you have a double bonded oxygen in the middle. So most common aldehyde that we've probably heard of is formaldehyde, right? It's used as a preservative, tissue preservative. Common ketone would be acetone. So it's used in fingernail polish remover. Carboxylic acids. Common carboxylic acid is acetic acid, which is also known as vinegar. So now we have both a double bonded oxygen and an alcohol group. This is what makes it an acid. You have to have both. Then we have esters, where we have the double bonded oxygen, and now we have it connected to an oxygen that has another carbon group on it. So we're just kind of increasing the complexity of our compounds. Esters are very pleasant smelling. Thiols are not. Thiol compounds are what's found in eggs, like when eggs go rotten, or skunks, how they have that very distinctive odor. That's because of thiol compounds. Esters are very pleasant in smell. A lot of perfumes have esters from, fruits and flowers, etc. Then we have amides. So we have our double bond O, and then that's going to be connected to a nitrogen. It can either have hydrogens or it can have other carbon groups coming off of it. Amide bonds are very important because this is your basic building block for your proteins in your body. So you have repeating units of a C double bond O N to another C to a C double bond O N, repeat, 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 we get polypeptides. And then we have acid chlorides, which are used in synthesis of other compounds.